welcome Manuela and Campanelli from Rochester Institute of Technology. Manuela is one of the leading experts in numerical relativity and computational astrophysics worldwide. She did her PhD in
Bern,
yeah.
Switzerland.
Spent postdoctoral time in Germany at the Albert Einstein Institute, moved on to Brownsville, University of Brownsville, and is now at the University of Rochester Institute of Technology. And today she will be telling us about merging black holes in astrophysics, not just. I wonder where else black holes might be merged.
Okay, well, thank you very much for having me here today. I will be talking about black holes, but before I go into this, I need to kind of give the credits to a lot of the people who are collaborating with me on of the subjects that I'm going to be presenting to you today. So we have a large collaboration. Not all of it is concentrated at one institution. Those are the people who are more or less connected with my own group here. But also, I have a collaboration with Julian Krolik, who is an astrophysicist at Johns Hopkins University. So it's a two-institution collaboration, and now becoming a three-institution collaboration because another of my collaborators here, Scott Noble, who was a research faculty in my group, has got a faculty position at the University of Tulsa. So it's a three-institution collaboration so far that we have. Okay, so let me start. Well, we have to start with the assumption that there are black holes. Otherwise, I may just say I'm not giving this talk today. So assuming that there are black holes, and assuming that we actually see them. We see the black holes both at the centers of galaxies by looking at the motions of stars around the center of the galaxies, as well as again at the centers of galactic nuclei. But we also see stellar mass black holes when they are coupled, for example, to stars, and we see that gas from the stars gets basically, around black holes of stellar mass. So we're going to work with these two mostly. Although we think that there are intermediate mass black holes as well, we do not have firm observations of those yet. Of these black holes, the stronger evidence so far comes mostly from the supermassive black holes, because those, we do see them at the centers of practically each active galactic nucleus. We do expect that they will build up hierarchy from galaxy mergers, from the smaller structure to larger structure. And if mechanisms like dynamical stellar friction or torque from gas and gravitational slingshot can bring the pair of the black hole close enough, then we are going to subparsec scale. And we are going into the so-called gravitational wave-dominated regime. At that point, gravitational radiation is the most effective mechanism to bring these black holes down to merger. So we do unfortunately have few observations of results of subparsec dual nuclei nowadays. I'm not going to review them, just an example here of one of these black hole pairs. So we're talking about dual nuclei. Until very recently, there was a paper now published in Nature by Graham and al., where they have this interesting periodogram from the Catalina Transit Survey, where they can see an observed period here of 1,084 days, which as an interpretation is understood as an interpretation of a closed binary at subparsec scale. So in the gravitational radiation dominated regimes. So since then, there were maybe a couple more papers, similar papers where they have these observed periods, which can be interpreted as binary black holes in the closest regime. Okay, so in order to find out what happened when black hole mergers, we have to solve the Einstein's equations. And to do so in the gravitational dominated regime, we can use a variety of methods. When the black holes are far separated, we can use the so-called post-Newtonian approximation, which is a weak field, slow motion approximation. You have to do both approximation in this formalism. And then when the black holes get too close to each other, and too close will depend generally from the masses and the spins of the black holes. When they become too close, then you have to use full numerical relativity to model the binary black holes. At this stage, a huge burst of gravitational radiation will come up from the binary, and we, in numerical relativity, finding out that even larger numbers than 10% of the initial total mass can get radiated out in gravitational radiation, which is impressive. And finally, when the black holes get close to each other, you could use another approximation method. So you have a single rotating distorted Kerr black hole that you can treat with black hole perturbation theory. And if the orientation of the spins and the masses are not equal for some particular configuration, it may happen that the final black hole remnant may recoil from the whole structure, as I say, depending on the black hole masses and on the spins. So these binary black holes are ideal sources for gravitational radiation. Observatories use it for. Because even if you would calculate the luminosity out of these gravitational waves, you could find out that they outshine in brief moments of the merger more. Their energy is bigger than the luminosity is bigger than the luminosity of the entire universe. So it's amazing. In just few moments, you have these very powerful mergers emitting very powerful gravitational radiation. So here what I have is, you have seen probably this many, many times, is the characteristic amplitude versus observer frequency of the various detectors. We have here advanced LIGO, which is now operating. Just entered engineering runs, and hopefully soon to be doing in the first science run, which is very exciting. And the binary black hole definitely is an ideal source, although LIGO will bet more on neutron stars binary in this case, because we do see neutron star binary in the sky. We do not see binary black holes of solar mass type yet. But if binary black holes of solar size type exist, then they are the strongest source. And now it depends how many of those. We do expect maybe more than 10 per year, depending whether you are optimistic or pessimistic. But this is a conservative number, about 10. You quoted this morning 20 in average per year. So definitely something very exciting is coming into our way in the next few years. We're talking maybe, definitely the lifetime of a graduate student here. So for LISA, we have to wait more. I mean, you have to be an undergrad student really to enjoy this probably, because this has been now pushed really, really far away. It's almost becoming science fiction here. But anyway, if LISA would have flown out, and it would have targeted those supermassive black holes of 10 to the 6, 10 to the 7 solar masses. And then we have, of course, a pulsar timing array, which is actually observing now and is getting to the accuracy levels that we may soon actually detect the very supermassive black holes. We're talking about the 10 to the 9 or bigger supermassive black hole in this case. And with pulsar timing array, we're really going to look at the weak gravitational field. I mean, we're looking in the so-called post-Newtonian regime. We're not going to look at the merger itself. Okay? But I'm really interested about something else here. What about if you have a pair of supermassive black holes at the center of galaxies, and there is enough gas around it, like in AGNs, and assume that they all carry either a circumbinary accretion disk around them. And then you could imagine that in this scenario, there will be considerable shocks delivered to the gas because the binary black hole during the black hole merger. And so you could imagine that there could be some interesting electromagnetic signatures that we may want to identify and therefore characterize and distinguish especially this signature from the characteristic AGN signature. Okay, so the idea here is to look whether we can find some particular characteristic signals that can be distinguished from the normal AGN signatures, and maybe look for them with telescopes like the Large Synoptic Survey Telescope or other telescopes like Pan-STARRS. And if you can do that, then you could combine electromagnetic astronomy with gravitational wave astronomy, and you can, so, well, this is a big word, right? The so-called multi-messenger astronomy that we use often in talks, but it may actually become the future of astronomy if we have both gravitational wave detections and electromagnetic detection, especially in the case of supermassive black holes. If you have both detectors, you should be able to do so. And then if you're able to combine information from these gravitational wave detectors, such as, for example, one day LISA, this is dying on me, and maybe other electromagnetic synoptic survey like LSST, then you could do interesting things. Not only you could do, of course, better localization, and you could have independent localization. You could also nail down the distance versus redshift relationship, and then you can treat these supermassive black holes binary as cosmological standard sirens. So, and then there could also be various interesting implications for gravity models and the relativistic accretion, jet formation, and so on. So you could associate MHD, magnetohydrodynamics effect, and accretion disk physics and its effect, and the effect of gravity on it. Okay. Okay. So, in order to to do the merger to black holes, you have to solve the Einstein equations. So, this has been a long journey. From, some of us here were not even born at this stage. I'm listing this because I found it very funny. This is in a conference. This is a summary of a conference, the first GR conference from, I think I will use the handmade, this is that, GR1 conference at the University of North Carolina. And Charlie Meissner, one of the big book, Gravitation, right? Look at what he said here. First, we assume that you have a computing machine better than anything we have now, and many programmers and a lot of money, right? So that's exactly what happened later on. How could he have predicted that? And then either the programmer will shoot himself or the machine will blow up. Somehow it's exactly what happened. It took quite a lot of time to actually merge these black holes. It took more than 50 plus years. So there's been quite a lot of effort in the field, and this doesn't make any justice to the field, but because I want to get to tell you about what happens to circumbinary disk and accretion around black holes, I will put just one slide reviewing a little bit the numerical relativity field. But from the 60s, from the collisions of two head-on, well, at that time it wasn't even called numerical relativity, it was called geometrodynamics. But then it became really numerical effort with the pioneering efforts of Smar and Epley. And that's when the supercomputer entered into the business the first time. And it is around the same time that later around when LIGO moved forward in the 90s, that the supercomputer centers were also funded. Okay, so these big supercomputer centers that we have, at least in the US. So it was a big thing here. There were, in the meantime, a lot of advances that happened during these years that we're laying down the foundation. So foundations, how you treat the black hole interior, for example. Do you excise it or not? What type of formulations of the Einstein's equations we have to take in order to solve these equations on supercomputers and so on. At some point, people said, well, okay, we have LIGO coming on. It's time, and we have the supercomputer. Let's get together and form this big grand challenge group, and let's solve the problem, right? And we'll all know how the story ended, right? It's like the joke I presented in the first slide. Yeah, the computer didn't explode, but more or less, right? And so Kip made a bet here. I don't know if he ever conceived, but this, he made a bet in 2002. He almost lost faith, right, in numerical relativists. They said, I have bet that this numerical relativist, the gravitational wave will be detected from the black hole collision before their computation is sophisticated enough to simulate them. In a way, he is right, because I don't know, he won't conceive, because, I mean, look, he put this, right, before their computation are sophisticated enough. So what do you mean, right? Maybe, maybe we have to wait, for SPEC to deliver, all the waveforms, so before you can conceive to that. But certainly he didn't conceive after this, right? After the 2005 breakthrough. Although he was very happy, I think, about this, right? And everybody was happy about that this has happened. But now, this, 350 orbits. I mean, this is amazing. Yeah, you have something to say?
150 cycles.
Cycles? Okay. I'll correct that. Okay. So factor 2 there, huh? Okay. So, but anyway, it's still impressive. It's very impressive, right? So, so what do we have today? We have this spectral Einstein code, which Harald is working on, which is basically descendants of the Pretorius generalized harmonic approach. And then we have the moving puncture codes, which are based on the Bunker-Shapiro BSSN 3+1 formulation. So how the numerical relativity community works so far? Well, we work in teams now. I mean, there is this SPEC team, the XSS, you could choose a better name than that, XSS collaboration, right, that we have here. Oh, it was Kip? Okay. So, okay, it's recorded, right? Okay. And there are also other collaborations. For the moving puncture, we have this, for example, the Einstein Toolkit, which is an open source collections of codes that are based on this Bunker-Shapiro code. And so a lot of people actually commit to this, commit their codes here. They're available, so you can use that. Most of the people were doing vacuum. Not all of them moved into doing GR coupled with magnetodynamics. Okay, so that's what I'm going to talk at some point. Okay, I have to put these slides, right? This is Harald's paper. It's just impressive, the number of waveforms that they can generate, and very accurately. There are still many challenges. Not all of them have been addressed. This one is 2011, right? It's 1 to 100. Still remain quite, and not obsolete in terms of what you can do today with numerical relativity, because it's a very challenging simulation. You have to use 15 level of mesh refinement. And here, in order to do this, it's not that people cheated, but they were guided by black hole perturbation theory on where to place these mesh refinements. Without that, you couldn't do it. Okay, so the big thing about black holes, right? We are in vacuum still. When you're in vacuum, the interesting physics comes mostly from spins, right? So in this case, I'm just reviewing the discovery of the kicks, as you probably know about that. We know that when the black holes have spins that are aligned with the orbital angular momentum, there is no kick, but they do radiate quite a lot of gravitational radiation. Okay. It can be even higher for, I think, Geoffrey, I think, has a paper where it can show that it's even 12% or so, I think. So it's higher. So, but what happens is that because of spin orbit coupling, these binary black hole will orbit around each other for quite a long time until they get rid of the excess angular momentum, and then they can emerge. When the spins are non-aligned, though, another interesting phenomena happen, and this is the case where you also get precession. Okay, we heard this morning to your thesis defense. In this case, you can get, for certain type of configuration, or for example, when the spins are lying in the orbital plane, or they are more or less a 45 degree with respect to the orbital angular momentum, you can get these very huge kicks, all right, huge in terms of, ejection velocity from the galaxy, obviously not in terms of speed of light, right? But it's still very huge, and so they have really a big effect in terms of consequences of growth supermassive black holes and formation of intermediate mass black holes. So the question is, where are they? All right? So where are they? There are a number of plausible sources, like, for example, this one now is old, but it's still one of the few that has resisted the criticism of the community, these double peak narrow line emitters from Commosa. There are other observations, I haven't listed them, but, side galactic nuclei, displaced active galactic, a number of them, X-ray, F-glow, feedback tree. In practice, there are a number of them, but they are all kind of in the, there may be kick, but we do not have a, we have also other possible interpretation of these things. It could be a binary and so on. And because most of these things depends also on the gas that is around them, then it's become important to being able to model the system with the accretion disk in a realistic way in order to actually determine whether you have really kicks or a binary black hole and so on. Okay, so now the question is that when you have gas, there is an effect, which is, especially if you have MHD, then you can transport angular momentum outward. Okay, and then when you do that, okay, so and then it tends to also align this is the torque exerted by the gas. It's called Martin-Pedersen effect. It tends to align the spins with the orbital angular momentum. Okay, there's a serious paper here. You can see up to this paper 2013 here that find that it's very efficient. Very efficiently, you can, if you have an accretion disk, really align the disk with the orbital angular momentum. Okay. So then there are other things like resonance effects here that can do a similar thing. So to say, well, okay, that solved the problem. That's why we don't see the kicks. The truth is, there is another paper just about a few weeks ago now, which reopened the entire question in terms of, do you have, in even the case where you have gas around the binaries, do you really align the spins with the orbital angular momentum? So in this paper, this is Gerosa et al. 2015, in case you haven't seen it, and a member of my group is on the paper too, so that's why I'm also excited, but it's also because it is opening a new hope for this large kick to happen, right? So what happens here? they find that this case with the black holes, when one of the black holes is counteraligned and the other one is aligned, okay, depending on the mass ratio, okay, they find an instability, okay? So any small perturbation, whatever perturbation, it could be a star, small, infinitesimally small perturbation will tend to basically, remove this perfect alignment, and it will grow quickly into a non-aligned binary. And so you, again, go back to the situation where you may have, precession, and you have precession, you may have, at some point, the binary, when it gets close enough, and the spins are maybe oriented in a certain way that can lead to these large kicks, okay? So this, again, opened the possibility for that. Is interesting. Another interesting thing that happens with black hole spins, this is, again, another paper from Carlos Losso, who is in my group. This is a rather long simulation. You can see the simulation. It's going on for quite a long time. It showed the spins of the black holes. They are precessing. What happened here, it's a phenomenon that the author called the spin flip-flop, because one of the black holes will, and you will see it at some point, is the black arrow, I think, in a movie, the right one, will reverse completely the spin, okay? It goes from, so up and then down, and it does it in this fashion, okay? So, and that is quite interesting, and it's an effect that is happening during the Inspiral regime. So it can, although they have done a numerical simulation to verify this, really this is a post-Newtonian effect, okay? And it's due to basically a conserved quantity dot product between the spin and the angular momentum. So it's really a post-Newtonian, conservative post-Newtonian effect. And an interesting thing here that happens is that if you can imagine now, you have these black holes. They are orbiting around each other. They have a big disk around a circumbinary disk, and they may have mini disks associated with each of the black holes, because we're going to see some gas gets into the regions where the black holes are. So they form this mini disk, and the spin of the black hole change. So the gas, so the accretion disk will go from prograde to retrograde. Okay, so this can cause some interesting shocks, and the dynamical timescale for this to happen is shorter than the gravitational timescale. So even the gas-driven alignment process may be not effective at resolving this. But now we also have the other paper, okay, which can tell you, well, maybe there are scenarios where the spins are not going to get aligned due to gas-driven alignment processes. So that's exciting from my perspective, because now you want to go ahead and try to see what happened to the accretion disk that's around the system. Okay, so if you have shocks in the gas, what you would like ideally to do, as I said before, is to actually calculate characteristic signatures, EM signatures, that are different from the signatures that, for example, emitted from normal AGNs, right? You want something that has some characteristics associated with the binary. So now the problem is complicated here, because you need accurate simulations of the source, both temporary variability and energy spectrum. So if you want to really start from the beginning, you're starting from galaxy merger and you're going down to when the black hole merges. So that's an impossible problem to do, right? Because look at the scales, right? So we are not going to solve this just with one code, one approach. We'll have to solve this by taking different simulations in different regimes and trying to connect them together, okay? So for the rest of the talk, I'm going to concentrate in this region here, okay, in the Inspiral regime. And that's a regime where you have enough orbits that they can do interesting things to the dynamics of the gas. But you also, it's also the regime where you have strong field gravity, okay? well, not as strong as in the merger, but it is still emitting gravitational radiation. So I'm going to concentrate here from now on. Here you can deal with Newtonian gravity. This can only be dealt with numerical activity. Okay? So there are many simulations in this regime. Okay? As far as I know, we are the only group dealing with this. There are a few dealing with this, but they do not have their initial condition to start over. Okay, so what do you need to do in order to do this? Okay, first, you need MHD. Okay, why you need MHD? Because of angular momentum transport. Okay, so you want to do that right. You need 3D, okay? Well, first of all, because real life is in 3D, well, 4D with time, okay? But also because if you cannot sustain turbulence in 2D. Gravity, you can use, depending on where you are here in this diagram, you can use either Newtonian, post-Newtonian, or full GR toward the end. You also need thermodynamics. Now that's the difficult part. That's a lot of the physics center here. You are generating heat. That heat gets radiated somehow. Okay, so you either do full radiation transport, which is a complicated business, or you do some kind of approximation to deal with the cooling of the gas, okay? Eventually, though, you would need to do full radiation transport to model this phenomenon in order to compute spectra and so on, okay? So we are not yet doing that. We are doing cooling, okay? Okay. Before I go into our simulation, I want just to review a little bit of what happens in this field. I've been working in numerical activity for as long as I can remember. But about 6 years ago, I got interested in this problem. And because of why? Because they were, until a few years ago, okay, the understanding was from 2D simulations, Newtonian binary, is that if you have a binary, okay, in 2D, or even UD, 1D, even people did very simple models there, you show that basically the binary, okay, exert a torque to the gas and vacate the region. And so people, were thinking, well, there is nothing interesting if you have binary. There's not going to be any electromagnetic signal whatsoever because gas gets pushed out, and there is no way you can generate any electromagnetic signal from merging black holes, right? So things change it. Okay, they change it a little bit with the 2D simulations where they find a little bit of leakage fraction, but they really changed it when we went to MHD, okay? When we went to MHD, because MHD is responsible, magnetic stresses are responsible for transporting angular momentum, it does push the gas across the gap, okay? And so you get really, the result that actually accretion never really stops until the binary is orbiting too fast, okay, that the accretion is decoupled from the binary. But until then, accretion continuously goes on. Okay, so there have been, therefore, this is an interesting simulation that I want to mention here. There have been, this is one of the most recent simulation, I think from 2014 from Paris, which actually confirmed this picture. But here they're not using MHD, they're using 2D viscous hydro simulation in order to, because these simulations are still very expensive, and they do find and confirm this picture that basically the gas efficiently really enter the cavity along these streams, okay? And what happens, and we're gonna see the movies, the gas falls in, it's accreting everywhere, but mostly around these streams. The streams hits the inner walls of the cavity, okay, and as it hits this inner wall of the cavity, they generate an overdensity here, okay, an axisymmetric mode, which will orbit at a characteristic frequency. And every time that it will hit one of these streams, dense streams, it will generate a signal. We're going to see that's what we found in this paper with Noble et al. There are also simulations that deal with the last portion of the merger. Again, this is amazing work because of the complexity that goes into this. So you have full general relativity MHD. However, one of the limitations of this work is that you are limited to few orbits because it's extremely expensive to run these things. And you also do not have the proper initial condition to deal with the system astrophysically. But still, they are finding quite interesting scenarios where they are finding, for example, this double jet structure that arise from the black holes and so on, okay? I just want to mention that briefly. Okay, but the real regime I'm really interested is the Inspiral. Why is it the Inspiral? Because, again, you have long enough, this binary will orbit long enough, and still relativistic effects will play a role. And so there is this paper also by my collaborator and his postdoc, Rudy Furtander here, who found that, you know, through some simple analytical estimate, they would expect a notch in the thermal spectrum and also a very hard X-ray bump from this analytical estimation. That's more or less going to happen when the binary are in spiral around each other. So you really need to be in that regime in order to see some interesting distinguishable effect. So, signal. So, okay, so what do we do in order to model our GR-MHD accretion? So I mentioned a little bit of the elements that you need. We're using this code which Scott Noble developed, which is called, and Charles Gami, by the way, also University of Illinois. He actually was the originator, and Scott Noble took it over and then generated this to handle binary black hole. This is a well-seasoned code. It's been used for many, many years to do accretion disk physics in full MHD. And what we did was to actually change the code that instead of taking just, for example, the space-time of a Kerr black hole, it's capable now of handling a binary black hole, okay? So you have to just make sure that when you solve your MHD equation, this G here is the G of a binary black hole space-time, okay? So, and then the rest is a GR-MHD code, is a coordinate code, there's a Lyrian code, high resolution capturing. It does have an ideal MHD, which is reasonably good enough for this type of simulations and so on. It's one important approximation that we do, okay, because we have dynamical GR, okay, but our accretion disk is a thin accretion disk. So, you know, the mass of this disk is not big enough to influence the space-time, okay? So basically, that's the only approximation we're doing, but that's a realistic kind of scenario for this type of simulations. So this is quantity H over R, so therefore it's of the order of 0.1, which is this more or less the size, tell you the size of the disk, okay? And then you can use various initial data like colloidal magnetic fields to follow density contour and so on into the code. Okay, so this is a paper that we did in 2012. We took 2.5 post-Newtonian space-time. Here, at that stage, when we published this paper, we had to excise the region close to the black holes, and unfortunately, we could not follow what happens in here. The reasons why is because you have a post-Newtonian space-time. So it doesn't cover the region close to the black holes, okay? But at that time, when we did that simulation, we already found some interesting results. And let me just go to these results. So this can go on. You see how many orbits we do. I mean, we can I think I'll move on, and then if you want to watch the movie later, we can. I mean, it's really go on for forever. I want to just show you the results, okay? So what we found is the following, okay? So again, we also find that the accretion never really stopped until decoupling, and decoupling really happened very, very almost close to merger, okay? So it happens, late enough. And by the way, these black holes that we took in here are separated about 20 m, okay? 20 m, where I'm using the geometrized units. So if you want to convert that, 1 m equal Rg, where Rg is the Schwarzschild radius, okay? So, so what we find is the following. Accretion continues until decoupling. Decoupling basically happened at very close separations, almost close to merger. And then we found these streams similar to the simulation that we've seen before, which was only viscous hydro. This is a full MHD simulation, okay, in 3D. We find these streams goes into the black holes, and we found a lump of material that builds up, okay, which has a characteristic signal and periodicity, okay? And the peak of this lump is basically the omega binaries minus the frequency of the lump, okay? And has a characteristic signature, okay? This was an equal mass. I'm going to show you now what happens later, okay? So we found this, and we thought, well, great. This is one of these characteristic signals that we want to see, right? So because, you should never 100% always, believe your simulation, you should always test yourself, right? What happens if I have a larger disk? What happens if I have a mass ratio, right? I'm going to get the same signal, right? What happens if I'm going to large separation? What happens if instead of 2.5 pn gravity, I have, 1 pn gravity? Okay, first question. What happens if you have only a less accurate post-Newtonian model, okay? Well, this was actually a good answer. So you can see that there is a difference in terms of binary torque, right? This is up to 40 m. There's, the binary torque obviously increase as you go to smaller separation. And by the way, this is only a hydro simulation, because really to find out what happens to what the space-time does to the gas, you want to do hydro simulations. So that's the only mechanism that push the gas around is, is gravity. There's no MHD. There's no MHD physics that complicate things. And so we found that basically there is no difference between the 1 pn model and 2.5 pn models, even around the 20 m. Especially after you have equilibrated. What does it mean, equilibration? You have to wait for the initial transients to kind of, resolve themselves, and so you have to do in some kind of quasi-steady state. You can see that after a certain point here, these 2 plus are practically the same, right? So this is the surface density. Okay, which is the surface density, is this quantity is basically the density integrated over this axis. Okay, so you can see that 1 pn and 2 pn practically make no difference. The only difference that you can see is that actually 2.5 pn, more accurate gravity model, seems to actually get to the quasi-steady state faster. So it's better in that. Now, I don't have a plot here, but if you go to smaller separation, then that really, you can see that that's when gravity starts to really make a difference, okay? So 20 m is the closest separation that we can safely handle with this without having any effects from the inaccuracy of your gravity model. Okay, so the next question we have, this is still work in progress. We have looked at this lump that formed, and we have done studies of mass ratio. We have injected more magnetic flux in our initial data. And we have also taken a larger disk than the one that we have. And in all this situation, we find that actually the lump, it's not excited as strongly as we had in that original paper. So it does depend critically on these initial data, okay? So that's bad news or good news, depending on whether you want to interpret this as a characteristic to the system. But, okay, so that's the finding. So, okay, so we're back in business. So now, okay, so if the lump is not generic enough, and we cannot therefore use that as a way, a mechanism to detect binary black holes in electromagnetic spectrum, what do we do? There's still quite a lot of interesting things that I think may happen. And most of the signals that we expect really to happen are in the interaction between, again, these highly dense streams, okay, which seems to be instead a generic feature, okay, and the wall of the cavity. So there is a continuous interaction going on there. So that's where we think most of the signal can come in. But also, some of the signal will come in when the two black holes get close enough that their inner disks start to interact. Okay? So that's when we expect things. But in order to model that, we need to put the black holes on the grid. And because we had a post-Newtonian approach, we couldn't do that. So here's what we did. We constructed, so we call this placing black hole on the grid, we call it BHRG, which means is actually constructing a space-time. Remember, because our G there that enters in the image D equation is a dynamical space-time, but is analytical space-time. In the Inspiral regime, you can do that. So we are constructing a new approximate global space-time. And we're doing it this way, okay? So this is more or less a diagram. These are the two black holes. We are treating the regions of the close to the black holes here with black hole perturbation theory, tidally deformed black holes, okay? And we call this the inner zone. And in the far region here, post-Newtonian theory is valid, okay? And here, over here, you use post-Minkowskian approximation. And that you have some buffer zones in between, you know, these regions. And now this is highly technical. I'm not going to go into details, but you apply some technique which is called asymptotic matching to basically match all these regions together and build a global space-time, okay, which is an analytical global space-time valid in the Inspiral regime. And you can actually, so we published this in 2014 here, and I have a graduate student here, Ireland, who is actually generalizing this now to spinning black holes, okay? So, how am I doing with time? Oh, it's over there. So I have to run really quickly. This is a study that we did again to look at what happens when you transition from Inspiral to merger. Eventually, when you get to binary, it's so close to merger, you do not want to continue with this global approximate spacetime. You have to do full GRMHD. But then you have the right condition, the right initial data to take over, right? So that's what we did, some studies to look at whether, you know, you take over from this global space-time with full numerical relativity. Do you get some eccentricity because of the inaccuracy of the data and so on? And we show that actually we are capable of removing the eccentricity very well, and, you know, there's no problem. Okay? Okay. So another thing that you have to do when you're dealing with black holes on the grid, you have to resolve the black holes. Now remember, you have the scale of the larger disk. You have the black holes. So we developed something which we call warped grid or double fisheye, which, by the way, is not only, you know, applicable to our code of environment. And you can see it's applicable to any code if people want to use it. It concentrates the grid points close to the black holes. So you see that the grid dynamically adapts to the system. So, okay, so we have that. Another thing that we're actually doing in order to deal with the black hole in the grid is actually to develop multi-patch code framework implemented in Harm 3D. Okay, so now again, this is it's highly technical, but we want to do it in a way that we can place the patches around each of the black holes, but also one of the things I didn't mention, we are working with a spherical code, so we have a problem. We'll say a problem. We have an origin issue, right, to deal. So we need to put a patch there too to cover the origin. Although there may be some analytical way to handle that, but I think that's a way to do it. Also because that way your time stepping is not getting too small, and you have to watch for that. Okay, so we do that. Here, so we can use, we have implemented this now in Hydro. It's been tested, it's working. We are moving into implementing this in full GR MHD. Okay, so this one now is a work of another of my PhD student, Dennis Bowen. The other thing we have to do, it takes still a long time to form these mini disks around each of the black holes, okay? So ideally, what you want to have is this circumbinary disk and then place, through initial condition, some disks, okay, around each of these, and then let it go and equilibrate it naturally, okay? Because accreting gas around these mini disks with full MHD takes quite a long time, and it's expensive, while it's much less expensive to equilibrate them. Now, we have a Newtonian theory work that gives us estimates of where the truncation radius for these mini disks should be, okay? And so my student here has been actually investigating, and this is to see where this truncation radius is when you move into the relativistic regime. So he's taken, for example, separations of 100M, in this case in his binaries, okay, and he's looking at whether the Newtonian estimate at 100M agree with his simulation. And he's finding very, very good agreement, as shown in this plot in this case. At the moment, so therefore at 100M of separation, the system, the mini disks really behave in Newtonian. This is a simulations that you can, where you see this mini disk as well as the larger disk. Remember that in this case, this is hydro, so gravity is pushing the gas. There's no MHD yet in these simulations, okay? Our intention here is only to see where the truncation radius of the mini disk is. And this is a simulation done at 100M of separation, okay? And it goes on for many, many orbital times. And we see that actually it equilibrates rather quickly around what we think it should be the solution. This is an unequal mass case scenario. Again, at these separations, it does agree fairly well with the Newtonian estimates. Okay, so the next step for us now is to take this prescription and to evolve this into binary with closer separation and to see how this truncation radius change, right? So then you can bring your MHD simulation, the full MHD simulation, to separation that are manageable. Because remember, I mean, even one of these simulations, even if we don't evolve the space-time, okay, MHD is very expensive. One of these simulations, okay, would cost about a few million CPU hours. So it's kind of expensive. We are doing many orbits. We have to do many orbits, okay? So, so what do we do in order to save computational time? We have to develop all this strategy once, have an analytical approximate space-time, so you don't have to solve the Einstein's equation, obviously, because you don't need to in the Inspiral regime. You have to resolve the black holes on the grid, so you have to, we use this double fisheye, or we use these multi-patch to cover the regions. And then you have to put this mini disk in place and then wait for their equilibration, because forming the mini disk, it's practically impossible, okay? This is a simulation which, unfortunately, my laptop, it's not wanting to run because it's too big. But I'm going to see if, this is one of our earlier simulation in full MHD. No, that's not the one I wanted. This is a full MHD simulation. And in this simulation, my laptop doesn't want to. Anyway, there's a binary here. You can't see it. It's so small. That's a larger disk. Okay, so it's going on. So you can see the streams. It tried to form the mini disks here, but we ran out of the computer resources. So we want to now place the mini disk in this around the black holes and then let it go. So you can see here the enhanced version. This is the full MHD one. And by the way, in order to try to build the mini disk, we have enhanced the magnetic fields to push the gas inwards stronger to see if we could build it faster, but even that. Okay, so so I think we have now this prescription to put the mini disk in there, and you know, now we have to just put things together. And unfortunately, I don't have the my millennia simulation, final simulation to show you, but it sounds like pretty exciting that we have all these elements now, and we're working together and putting all these things together. The only missing elements that we haven't really touched yet is the radiation transfer, although we have a post-processing radiation transfer tool developed by Jeremy Schnittman that can calculate spectra. Okay, so I'm about time, I believe. And I just want to conclude. So we, I think the field of numerical activity, it's delivered a number of results, and we are there working really hard to calculate these gravitational waveforms. There has been a number of interesting results coming from numerical activity that are interesting from the point of view of astrophysics, especially when we talk about gravitation, radiation, recoils. The future is bright, right? We know that. But I think there is much more work to do in really modeling this black holes binary. If you consider a realistic scenario where you have, in some realistic scenario, gas and or even stars and objects around it. So that, I think, but that it's a different principle, a different regime than just a merger or close to merger, especially in the Inspiral regime. I think it's quite interesting that you can, you know, get some interesting electromagnetic signature there, because if you can then calculate this signature and calculate the gravitational wave signals, you can combine the two and maybe do some interesting astrophysics. But even if you don't have gravitational wave detectors, maybe that's the only way we can really detect supermassive black holes at the core, binary supermassive black holes at the cores of galaxies. Maybe that's the only way until 2034. Okay. So I think that's very exciting. It's a new field. Anyone who is interested, please contact me. There are very few people working on this right now. It's just, I think there's some people in Illinois, to Shapiro, as I mentioned before, our group, maybe Louis Lenner at the perimeter did something, but not many of us. Okay, well, thank you.
Yes. So you showed that
lowering the PN order didn't make a difference in the hydro simulations in one of your earlier runs. I'm wondering if instead of using full GR, just using Newtonian plus some prescription for the black holes, which guarantees that gas might fall into black holes at some modified Newtonian potential that has a point of no return. Is that something that's plausible for handling these computational challenges?
Let me show you what I briefly had to skim through. There was a simulation by Faris just of last year where people have actually handled the black hole that way. Okay, let me see. If I can go back to the paper in question. This one. Here is that they have two things, basically. However, they will not be able to model what happened to close to the black holes because they don't have black hole horizon. The other, this is an impressive paper, I may say before, but there are two shortcomings here. One shortcoming is that in this particular case, they have used 2D alpha disk simulations. Now, alpha disk models are reasonably good at, giving you, qualitative features, but they really get things wrong when it goes down to properly model angular momentum transport in the disk. For that, you really need MHD, okay, in 3D. Okay, so that's one of the shortcomings. In fact, they do find qualitative feature, like, for example, this lump, but this lump is actually not even moving in their case, while in MHD case that we're finding is actually orbiting a Keplerian frequency. So that's one of, for example, the differences. But that's one of the things. There's been several papers, for example, from Julian Kralik, who have demonstrated that you get really different results, between quantitative results between MHD and alpha disk. So that's one shortcoming. The other shortcoming is the one that I mentioned. You can do that with two things. In Newtonian theory, and maybe just Inspiral them down, right? And you can get reasonably good, interesting physics, as you can see. For example, the fact that you're forming mini-disks, their size in agreement also with analytic predictions, similar to what we're finding with our student in this case. But one of the other thing is that Newtonian is scale-free, so at which point, you really can't, really deal with the relativistic regime in this case. Not really questionable. So I think it's interesting, but it's qualitatively interesting. You need, and again, you need the black hole horizon. If you want to measure, for example, accretion through the black hole horizon from these mini-disks, nobody has done that so far because you don't have the black holes. You can't do that. And then you want to find how the jet is generated. For example, you need a black hole there. Okay, so all of these things need the black hole to be on the grid, the real black holes. Yes?
So when you were talking about the formation of the lumps, you described 3 or 4 simulations where you vary different factors like the binary mass ratio, the separation, the circumbinary radius, and so on. Which of these factors did you find were the most important in determining whether the lump was formed or not?
Okay, that's a very interesting question. This is still under discussion with my collaborators. Okay. So where is that? So whatever I say here, comma, because I think we're still in discussion. This is very recent results. We're trying to write a paper before the summer ends. I can't move forward. I don't know what's happening. But what happens there is that we think that if you have a large magnetic field reservoir, okay, it tends to kind of move angular momentum around you know, more efficiently. And we think that this slump happened actually in regions where, you know, we lose a little bit of angular momentum transport of resolution. That's what's originating the lump. But we think that that may be the reasons that you have either more magnetic flux and thus do this, and you have a larger disk, or you have a larger reservoir to do that. So it may also be that you need to, the quasi-steady state for this other configuration is not reached around the same time as we had with the smaller disk. Okay, so you have to wait longer for this lump to build. And now we didn't have the resource to do, you know, the longer. So it may still be true that a lump may form at later times. Okay? But it's not certainly forming around the same time, the Nobel et al. Simulations. And it's weaker with the mass ratio. That you can certainly see. Yes, hi.
Black hole templates and the low latency searches at this stage?
The black hole templates?
Well, you know, the low latency searches that produce the EM alerts
Yes.
probably only going to have DNS forms. Should the mass range be expanded just in case?
Okay, so I haven't dealt with black holes from, you know, sources for LIGO because in this case, I am not sure how to have enough gas. I mean, these are, you know, gaseous environments. So I don't know, you know, whether an astrophysical system in the LIGO band will have enough gas or an accretion disk will survive long enough to generate interesting electromagnetic signature in those cases. But if it does, that would be probably an exceptional case, more an exceptional case than the routine, just because the way these things form. So that's why I'm working mostly with supermassive black holes in this case. But yeah, it could be interesting. Maybe you could. I mean, everything that we do here, you know, can be translated in principle to stellar-sized black holes, but you know, maybe not, because maybe the disks that are forming around these black holes are thick and not thin like we have here. So I do not know. I don't think we have a real understanding of the initial conditions around these systems at all. We have more understanding for the AGN type black holes. Okay. But it would be interesting. I don't know. Maybe you guys see the waveforms first and then see some wiggles. So I've seen a paper recently where they do, what they do is they do follow what happened to the, actually this is Matt Dues is doing that too, right? A black hole, if you have a black hole neutron star merger and you have a black hole and an accretion disk, the accretion disk can be massive enough to actually produce some interesting effects on the waveforms. So I think that's interesting. That could be interesting for EM follow-up.